questions, and I apologize for not getting that information out sooner about the last class. I had to go to Birmingham to UAB. I had some surgeries from a blood clot in this long story. I'm going with it. Anyway, any questions before I go?
Yeah.
There's no quiz. Yeah.
3.39 or it was given D equals 3AX plus
Say that again.
given D equals 3AX plus 2XY AY
2xy ay
plus 8x squared y cubed AZ centimeters per meter squared.
It's coulombs.
Coulombs, I'm sorry.
Coulombs per meter squared. Meter cube. No, coulombs per meter squared. Sorry.
And then it's determine the charge density at point P111. Find the total flux through the surface of a cube. 0.
We'll do that second part in a second. First of all, without saying the answer, how many know how to get charge density if you have D? 1, 2, 3. All right. This is so important. You'll have to know this. It's the divergence of D. It's rho V is equal to divergence of D. The divergence is the operation in the back pages or the back cover of your book, if you have a book. Now, the one you're going to have to know by heart, I'll give you the others, is the Cartesian coordinate version. So divergence of D in Cartesian coordinates is d dx of dx plus d dy of dy plus d dz of dz. If you look in the back of your book, you'll see this. There are two other coordinate systems they have. They have cylindrical and spherical. I would give you those, but this one you have to know. It's the easiest, the most obvious, right? You take a derivative of the respective axis scalars, the dx, dy, and dz, with respect to the axis that they're on, and just sum them up. Now it's a scalar. So just look here. What is rho v for r's? Take a look and do it in your head. The derivative of 3 with respect to x is what, class? 0, right? 3 is a constant. Take a derivative of any constant with respect to x, y, z, it's 0. Do you all agree with that? So it's 0 plus, now what's the derivative of 2xy with respect to y? Class? 2x, right. Now what's the the derivative, is this right, 8x squared y cubed?
That's right.
All right, what's the derivative of that with respect to z? 0. It's important to see that. So it's 2x. That's the volume charge density. Then they ask for the integral of d dot ds inside a region, right? Or they really ask for the integral of d dot ds over a surface, which is the same thing as the integral of divergence of d over the volume. Do you all follow me on that? If you take a surface integral over the entire surface of divergence of of d dot ds, it's the same thing as integrating all the charge. This is Gauss's law. This says the integral of d dot ds over any closed surface is the charge enclosed, which would be the divergence of d, the charge density integrated over the volume. You all with me? All right. Give me that surface again. Or the region, yeah.
It is 0 is less than or equal to x is less than or equal to 2.0.
All right, 2, and that's x?
Yes.
Oh, all right, I'm going to just call this x for now. Go ahead. Y?
It just gives x. It's a cube.
Oh, all right. So if it's a cube, I mean, we can do it a couple ways. I'm going to just do this in terms of the charge density. So now we're going to take, for the total charge, this would be Q enclosed in that surface, right? Do y'all agree? If you integrate divergence of D over the volume of that cube, it would be the charge inside the cube. Correct, class? So this is going to be a triple integral, and first I start with the charge density, 2x. The units of that would be coulombs per meter cubed, because d was coulombs per meter squared, so take another derivative, it's coulombs per meter cubed. And then the differential volume, that's simply dx, dy, and dz. Now this is a cube that's got one of it, I guess it's got its origin at 0, and it goes from 0 to 2, 0 to 2, 0 to 2 in the x, y, z directions. Agreed, class? All right, so when I do this integration, the x goes from 0 to 2, the y goes from 0 to 2, and the z goes from 0 to 2. Does everybody follow me on this? I'm just sticking the divergence of d as rho v in there, and I'm going to execute the integration. This would be the easiest way to do this, in my opinion, to do instead of the surface integrals, because there's 6 surfaces on the cube. So when you do this, what do you get? Well, maybe you want to do the surface thing. Well, when I integrate 2x dx with respect to x squared over 2 times 2, or just x squared, right? X squared evaluated from 0 to 2. 4. Do you all agree with that? So it's 4. That would be the x squared integration. Now, or the effects of it. Now when I go dy from 0 to 2, I get 2. And when I go z, dz from 0 to 2, I get 2 again. So this is 16 coulombs. Now you asked that question. This is a pretty good problem for a couple of reasons. It really, really showcases the ease of which you can integrate a volume charge density to get the total charge. Now, if we did the integral over the cubic surfaces, if you think about it, we got 6, right? Now, over the x cubed, I want you to just understand this. If I take a look, I shouldn't say x, if I take a look at this surface here, I'll try to explain this as simply as possible. If this is x, this is y, and this is z, and I have a cube like this, oops, I had to make my x positive there. Cube like this. Then this surface would have an ax vector. This surface would have a minus ax vector associated with it. The top surface positive ax, the bottom minus, right? Now look, when you integrate d dot ds, well, when I take the surface vector ds, it's in the ax direction, I dot it with this, I get 3, only 3. The other 2 components go away. Do y'all see that? So if I have 3 integrated ax over that surface, it's 3 times 2 times 2, or 4ax. Do you all follow me? And times, 3 times 2 times 2 is 12. It's 4 would be the area, 4 meters squared, and it would be times 3 because that's the coefficient. But look down here at the bottom surface. You see how ax is minus ax? It would still have the same resultant integral of 3 times the ds dy integration would be 3 times 4 because that's the surface area, but it'd be minus, they'd cancel. Do you all see that, class? This is one thing. Because the d vector is not a function of x, y, or z, I know that this integration would cancel the integration right below it. I know that just by looking. Now this one's interesting. 3xy ay. Where's that surface? Well, this is y, this would be the ay direction, and this surface element here would be equal to ay, right? And then it's going to be times dz dx, or dx dz. Y'all follow me, class? I'm just trying to make you aware of this. Now when you do this integration here, I'm going to have 2xy dotted into ay, which gives me 2xy, and it's then integrated over z and x. Well, the z integration doesn't affect this. Do y'all see that? So I would just get times 2. So it'd be really 4, because it's 2 in front there. 4, and then I would have to integrate dx. And dx integration will give me something, but what I want you to see is, as we're going around here, it's going to be a little more complicated to do that over every surface. Do y'all see that? You can do it, and I can talk my way through every surface. But for me, it's easier to do divergence of D. That's the one thing. I just wanted to show you, if it's a constant, it's easy. V's get a little more complicated. Y'all follow me, class? All right. What else did I ask in there? Anything you
That
want?
was it.
Okay. We can do the 6 phases, but it just is kind of takes a little time. All right. Any other questions before I get going? Remember this one thing: divergence of D is in the back cover of the book, and that's the thing that gives you the volume charge density. Period. And I gave you some problems. They weren't very hard. They're just applying Gauss's law, really divergence one, right? Okay. Now today, what I'm going to do, and since I want to try to give you a page book reference, we're going to work through potential. So this starts on page 167, then it's voltage, really what we're going for. And I'm going to try to explain this in a very practical way, something to give you insight. Okay, we're going to actually go to voltage. If you're an electrical engineer, you've got a pretty good idea what voltage is already. You've had your circuits course. You probably in high school know what it is, right? It's really electrical pressure. Also, voltage is really electrical pressure. Things that would make electrons or any kind of positive or negative charge move from one point to another. So the way voltage is actually explained from a physics perspective is they go back and they say, what if I had an electric field, E, in a region of charge? Assume it's uniform. And I take a little chunk of charge and I put it here. And I'm going to say my chunk of charge has got a value of Q. You don't have to write this down, really. You've had this probably several times, but if you want to, go ahead. Now, if there's a charge Q in an electric field, this field is going to be uniform. All right, follow me on this? Then there's going to be a force on this charge, an electrical force, right? And the electrical force is Q times E. Do y'all agree with that? And that force would be, in this case, if charge was in coulombs, and electric field in volts per meter, it would be in newtons. We don't have a good handle on newtons because we're electrical engineers. And generally speaking, in this country, we don't use this Newton as a measure of force. We use, technically we use pounds, but I guess more and more, yeah, they use kilograms, but kilograms is a mass. They equate pounds to kilograms because the acceleration is 9.8 meters per second squared here. So we do a lot of that kind of stuff in America. We mix things up. But newtons is really the force. All right, now, you know if you integrate force, right? Integrate force dot dl over any path length from 0 to L, what you actually get is the work that's done by that force. And I think everybody knows that. It is a dot product, so it's force dotted with the differential length and then the integral of that. Then it depends on the path. If I had a force, for instance, in this direction, and I moved something in this direction, perpendicular to it, the work would be 0. If I have a force in that direction, I move it along the direction of force, then I'll have either positive or negative work. Do y'all follow me on this? So just remember, path does make a difference. But anyway, if I take a look at this, force could be written as QE, so it would be the integral of Q come out front, the integral of E dot dl, and that would be from 0 to L, would be the work And I hope you understand, I'm trying to be as casual about this as I can because these are just general concepts. You integrate from 0 to L of the force, or just the vector E dot dl, and take Q out in front because it's a constant, it's a scalar. You get the work, right? Now that's the work the field would do. Do y'all follow me on that? That's the electric field that's doing the work. If I take this charge and I have an outside force and I push against it, then the work the field does would be negative the work that I'm doing. Do y'all follow me on that, class? All right, think about this. If the force is this way, if this charge is moving this way, the force is being allowed to push it, then the force is doing positive work caused by the electric field. And the external force would be doing negative work. However, if say I'm here and I push it this way, I'm the external force, then the field is doing what's called, quote, negative work. Do y'all follow me? At least the concept. Work can be positive or negative. So this is actually the work that the field does. What we do is divide that by Q, like so, and we call that the electrical pressure or voltage, but that isn't quite true because this is the electrical force the field did. You're always looking at the work related to the outside force. The outside force that would move it would do negative work. Are you with me? So, therefore, the way they equate the definition of voltage difference between 2 points, it has to do with an outside force moving something. Y'all with me? So what you're actually getting is potential for work to be done when you get this, and I'll explain more. The actual difference, or the definition of VAB is VA minus VB, and it's equal to the integral from B to A with a minus sign of E dot dl. I want to make sure I give this to you in your book so I don't confuse you. He does a little discussion of this. Oh, I'm sorry, he goes from me. My bad. Gotta make sure I get this notation. That's no problem. He does it this way. I had it right. I just want to keep his notation because my A that I had up there was his B, and his B was my A, and vice versa. So this is on page 168. And I'll explain what this actually means. Now, and this would be VBA. What this really means to me, and if I'm trying to explain this in the simplest terms, is if you have a voltmeter and you stick the positive lead of the meter there, and then the negative lead of the meter there, that's the voltage difference you'd read, right? Which means if you switch them, you would read a negative voltage. Now that is electrical pressure. So when you have electrical pressure, I'm just going to say that this is a plus to minus voltage, and it doesn't matter what it is. It means this: if you have any charge at all around this region, it will want to move from the positive to the negative if it's positive charge. And when you were taught circuits, you were taught that technically positive current left the terminal of the battery and the positive terminal and flowed back to the negative. Do y'all remember this? Right? Now, technically, what actually moves in wires? It's electrons, isn't it? Electrons move in the opposite direction, but we're talking about what's called positive current when we're dealing, or positive charge. We always assume it's positive charge. You don't move towards the negative potential from the positive. And this is the voltage. Best way to do this is with a simple example, because this will make sense to everybody, I think. If I just take a charge Q, centered at the origin, and I'm going to have some RA and then some RB. And let's make RB greater than RA for now. And this is a positive charge. Y'all follow me? So RA is closer. Now here's the deal. The closer you get to a positive charge, the greater the voltage is. I can prove this, but it's true. And I'm going to, as a matter of fact. So if you were to measure the voltage difference with RA positive and RB negative, you get a positive voltage. And just to prove that, or show that, let me erase this, show you what I'm talking about right here. When I do these things, when you talk about voltage, if you get a handle on the concept, the integration of E dot dl, if you're coming further away from a positive charge and getting closer to it, it is always positive. All right? It's always going to be positive. And if you're moving away, it's always negative for voltage. So anyway, let's just do this one. For this one, if I have my coordinate system, say this is centered at the origin right there, this charge, then I have the electric field from the charge would be radially away. It would be Q over 4 pi epsilon naught R squared in the AR direction. Do y'all agree with that? That's just the standard electric field from a single point charge at the origin, correct? Now, if I wanted the voltage between any 2 points, he likes going from B to A. I'm going to take the integral of minus Q over 4 pi epsilon naught R squared AR dot DL, which would be simply DR AR. There's 2 other terms, but the dot product would be 0, the other terms dotted into AR. And then for this one, it would go from A to B. All right, in this case, I'll say RA to RB. So when you do this, AR is 1, and I'm going to get a value that's going to be Q over 4 pi epsilon naught. And then when I integrate 1 over R squared, I get minus 1 over R, correct? So I have minus quantity 1 over R, evaluated from RA to RB. Here I'm just showing you the integration results. And this is what I always do. When I see a negative sign in front of something I'm going to be evaluating at 2 limits, the upper and lower limit, I get rid of it and switch the limits. That's what I always do. So when I do that, this becomes RA, and this becomes RB. Do y'all agree with that, class? Just switching the limits. And what does that become? Q over 4 pi epsilon naught. Then you have 1 over RA minus 1 over RB, right? That would be VBA. Think about it. Yeah, that's. Wait a second. that's technically right. But he has this. Oh, there it is. There's a minus sign here already. Yeah, these limits, I'm sorry, this right here is gonna have two minus signs. So actually it's gonna be RA here, RB. There was a minus sign here, I integrated, I get a minus 1 over R, the two minuses cancel, and then you'll get this, and this should be RB here, minus RA. I'm so sorry about that. Now the reason I'm making that point is, remember I said VB was further away, right, RB? So the positive lead would be placed here and the negative lead here. Now the truth is, the voltage difference, if I'm putting a positive here to here, has to be negative, because this is closer. Just, do y'all follow me on that? The closer you get, the higher the voltage is in a positive sense. As a matter of fact, what they usually do is this. The way I've done this, this voltage is going to be negative because I made that assumption right there. I'm going to show you something now that'll kind of help shed light on this. If I say that I want the difference, and I want to do it right here, okay, please focus on this part, because this will make it a little clearer. Suppose I'm going to get the difference as, but I'm not going to take RB as the positive. I'm going to take RA here, this point, as the positive. And let RB here, RB is going to go to infinity. So if I take a look at this, the voltage VA to infinity would be equal to the integral minus the integral, and it's going to be from infinity to A of Q over 4 pi epsilon naught R squared AR dot AR dr. Now I'm putting that down here because I'm putting A first here. In the book he puts B first, but I'm going to use my other limit as infinity. So I've got the same limits if you look in the book. This is here, this is here, there's a minus sign. I'm trying to do it exactly like he did. When you get this, it comes out to be equal to, I get a 1 over R squared integration, integrated is minus 1 over R with the minus sign is positive, and then I evaluate it. So I get basically Q over 4 pi epsilon naught, and then I get 1 over A minus 1 over infinity. Now, if you actually evaluate it, what's 1 over infinity? 0. So don't even write it down. And this is handy to know. This is the voltage, VA, assuming that at infinity it's 0. And because it's a finite charge, infinity being 0 is a great reference. Now, I think Irwin and whoever he had for circuits emphasized this. They said that anytime you're dealing with voltage, you have to have a reference. A measurement has to be with respect to something. When you had circuits, it was ground, right? He defined something termed ground, it meant the 0 voltage. And it's the same thing with voltage in general in any system. It doesn't matter if it's circuits or in general, and really the universe, there has to be some 0 reference. And when I have RB going to infinity here, I'm saying voltage at infinity equals 0. That's what I'm really doing. That's where it's 0. And that means VA is this. What's nice about this, if you have a voltage reference, this is reference to infinity, if I want the difference between any 2 points, RA and RB, I can find the voltage at A, assuming versus infinity, or this, and then I can get VB with respect to infinity and subtract the two and get the voltage difference. And you won't get confused with sign then. Y'all follow me, class? One thing I always remind myself of is the closer I'm getting to that charge, the greater the voltage is with respect to infinity. And I can always find the voltage difference between any 2 points by finding the voltage at each of those points with respect to infinity and subtracting it, okay? And that should go a long way, helping you guys. Now, when you're dealing with voltage, another thing I'm going to tell you about is there's 3 systems where we can calculate the voltage with typically used coordinate systems: Cartesian, cylindrical, and spherical. Spherical generally is a thing that's nice. It lends itself to simple kind of problems that you can easily execute with integrations like I showed you. Cylindrical has a little trick to it now and then, and Cartesian coordinates are just used usually for infinite planes, something where you want the voltage difference between points in infinite surfaces, planar surfaces. I'm saying this thing, well, I hope it's beneficial. So let me show you a few other things about calculating voltage. And then I want to also show you why it's so nice to get voltage instead of electric field from charge distributions. So suppose I have a infinite line charge, rho L, on the z-axis. I'm just going to put it up there. And I want you to think about this. I want the voltage difference, and I'm going to have a distance A perpendicular to that, and I'm going to have a second distance B perpendicular. And we're going to assume, I'm not going to put R sub B, I'm going to assume B is greater than A, so B's further away, right? If that's an infinite line charge, the electric field is going to point radially away, right? It's going to be in a direction perpendicular to the z-axis. It's radially away, or in the rho direction. Y'all agree with that? Now, if I put a charge here, plus charge here, think to yourself, which way would it want to move? Radially away that way, right? And if B was greater than A, it would be moving in the direction of B, correct, class, radially? Now, you don't care about any movement this way. You know why? There's no force on it. The force is only radially away. So any change in the altitude Z makes no difference. Do y'all follow me? So if we are getting this, if we want the voltage difference between these 2 points, technically, and he likes to use VBA, is VB minus VA. Therefore, B would be positive, and you would assume a negative value, wouldn't you, class? If B is further away, the positive lead in your meters here, and the negative leads here. Well, that's equal to the integral of the E field from an infinite line charge. What's the E field from an infinite line charge? Do you remember? Anyone? Rho L over 2 pi epsilon naught rho A rho. Do you remember? If you have an infinite line charge centered on the axis, that's the form of the electric field. How many remember that? Okay? You're going to have a pretty good working knowledge of this. It's going to have to be there when you get, especially for the test. You got to know this like the back of your hand kind of thing. All right, so I'm going to put that in there. The E field is rho L over 2 pi epsilon naught rho A rho dot DL. Well, DL, I only write the term that survives. I know DL technically is equal to D rho A rho plus rho D phi A phi plus DZ AZ. Do y'all follow me? But you see, this E field only has an A rho component, so I only bother writing the A rho portion of DL. So I just write D rho A rho right here. That would be the differential that survives. You with me? Now, where am I going? Well, there's actually a minus sign, right? And when you look at this, what happens is what? the B here would be here, and the A here would be here. And I'm doing Whitmore's notation. I can do that differently. Yeah, he likes B, A to B with a minus sign. Y'all with me, class? All right, let's do it. So for this one, I'm going to get minus rho L over 2 pi epsilon naught. Now A rho dot A rho is 1. And when I integrate 1 over rho, I get natural log, right? 1 over x dx, or 1 over rho d rho is integrated as natural log. Y'all know that, right? So it's natural log of B over A. And that's the voltage VB minus VA. Now if B is greater than A in magnitude, that's negative, isn't it? But doesn't that make sense? Because I say, when I'm doing this, if B is greater, I'm putting the positive lead in my meter here and the negative lead here, right? And remember, y'all know with batteries, right? If anybody's ever measured the car battery's potential, and you got the terminals wrong, was negative, right? Y'all remember these things? Right? Well, here, the potential from here to infinity is less than the potential from here to infinity, all right? So if I put the positive lead here, the negative lead here, it will be a negative voltage. Do y'all follow me on that? Okay, let me do it this way. If you got a battery, plus to minus 12 volts, okay? If you measure it, positively to the meter there, negatively to the meter there, here's my meter. If I put my positive on the positive, negative there, then it's going to read 12 volts, right? All right, now if I switch these terminals, it's going to read a negative, right? If I switch it. Y'all agree with me? Okay. Now think about what this is actually doing. It's measuring the voltage difference. I say, think of voltage difference with respect to infinity. Out here, the voltage difference between that infinity is less than this in infinity, right? Y'all with me on that? Can you all grasp? I'm trying to make sure. It's further away, right? From the axis of the charge, from the charge, right? That means this voltage is less. Call it minus, or call it 100 volts. Whatever this is going to be 100 plus change, 120 say, right? So if I measure 100 minus 120, I get minus 20 volts. Does that make sense? I'm trying to do this in a way that's meaningful, not just abstract. And I always keep my mind on what, the closer I get, the greater the voltage. So what about my leads? Here, if I put the positive lead to infinity, that voltage difference is less than here to infinity, right? Therefore, if I put the positive here to here, it's really subtracting the two voltages, I get a negative value. Which means, if it's negative, that's okay, you just have to know that. Right? And here's the trick with when you have any kind of infinite line charge, here's the problem. You can't measure the voltage difference between a line charge point away from it, an infinite line charge, and infinity. Because look what happens. Just like B go to infinity. Well, what happens to this? What's the log of infinity? Infinite, right? You would have an infinite voltage difference technically, all right? You follow me on that? And the reason you always get an infinite voltage is if this is an infinite line charge, you have an infinite amount of charge, don't you, class? Anytime you have infinite amount of charges involved, you're going to have a voltage at infinity that tends to infinity. There'll be an infinite difference between any finite point and the voltage at infinity. An infinite plane is the same way, if it's a truly infinite amount of charge. Y'all got that, class? These are tricks that I've learned over the years. So anytime you have a line charge with an infinite amount of charge on it, or a plane of charge, or a surface of charge, or a volume of charge that has an infinite amount of charge in it, then the voltage with respect to infinity from any finite point will be infinite. And therefore, it tells you have to measure the voltage with respect to some reference point that's at a finite distance from it. That's real important if you're going to have a reference, because it won't work otherwise. Now you can get away with it with point charges or finite amounts of charge. You can let infinity be the ground, if you will, it's the zero potential. There will be some problems I give you on this, but just remember, if you can get the electric field from these things, these charge distributions, you can always get the voltage, all right? There's something else that I want to mention too, before I close. Because he does this, but this is really useful. I can tell you. Really useful. So, don't write anything, just listen. So, if I have a charge, let's say this is a coordinate system, and I put a charge here, Q. I'm a distance r away, right? Well, I know that the E field from here is Q over 4 pi epsilon naught r squared AR. I'm going through this a little quick, right? Everybody knows that's the electric field from a point charge. Well, if I have any differential amount of charge, and this is dq, and if I have a vector r from that charge, then I'm going to have a differential electric field equal to dq over 4 pi epsilon naught r squared AR, and that makes perfect sense too. We'd have to get r and AR and stuff like that, but it still at least makes sense. We've covered that. Now, whenever I get an electric field, a differential electric field, to get the total electric field, I have to integrate the differential electric field over where the charge exists, Q, all charge, right? Remember the line charge integrals, the loop, right? We get a differential electric field, then we integrate it over the total line charge to get the total electric field on the axis, or over the length of the line if we want the electric field at a point radially away from an infinite line charge. But in general, the electric field has 3 coordinates, 3 components, I should say, and in general, these integrals are nasty for a lot of normal geometries. They get real nasty. However, if you had a finite amount of charge, and you wanted the differential voltage with respect to infinity, this right down, with respect to infinity, then I could say, if I have a differential charge dq, and I'm out a distance r away, I don't have a vector, I have the differential voltage would be equal to dq over 4 pi epsilon naught r. Now there's no AR, y'all follow me? There's no vector component, that's a scalar. Voltages are scalar terms. So if I wanted the total voltage from any charge distribution, assuming the voltage at infinity is 0, and it's best to make it 0. You're stupid if you don't, if you have a finite charge. Does you no good if you don't. Then you can say the total voltage would be equal to the differential voltage over the volume where the charge density exists, or the charge exists. That should make sense to you, right? Now that's a scalar. Hear me? A scalar integration. There's not 3 components. Nothing is hard. Suppose you get the voltage with respect to infinity, and you want the E field. This is the nicest thing in the world. Then you can say the electric field, write this down, is equal to minus the gradient operation times V. Now this is a scalar. This is a vector. Got me on this, guys? This is easy to do, the voltage, relatively speaking. It's easy to get V from a charge distribution. It's hard to get E in general, right? Now I'm going to prove it to you if I have time. So, what is the gradient operation? How many have your books there, or access to the book online? If you take a look at the back page of your book, you're going to see something that says gradient. It's an upside down triangle right next to something, probably V, but take a look at mine. It's right after divergence, gradient, and it'll have triangle V. And when you look at that in Cartesian coordinates, E is equal to I'm gonna put the minus sign here. dv dx ax plus dv dy ay plus dv dz az. Y'all with me? Okay, so how about proof that that's so much easier to get with voltage? The E field's easier to get with voltage than it is to get by doing those integrations. I'll show you probably, there's great examples, but probably the best one. Now you can do this only with finite amount of charge. Just remember that. If it's an infinite amount of charge, there's no guarantees. There's tricks you can do to get it, but no guarantees. All right, so this is sort of one of the classic examples of why it's so nice to have that. Suppose I have a loop of charge density of radius A, and it's in the XY plane. This would be X, this would be Y, this would be Z, and what I'm trying to do is show you this loop right here, and this has rho L on it. Now, you remember doing this thing with me before, right? Remember we got the electric field on the z-axis, correct, class? We made an argument of symmetry. We're going to get the volt. Do you all agree there's a finite amount of charge there? All right, so at infinity, we'll call it 0. And now I'm going to say that if this is my radius vector r, and r would be equal to, this would be at a height z, r would be equal to the square root of z squared plus a squared. I hope you can appreciate this as a straightforward observation, right? You're out a distance a, you're up a distance z. To the actual loop, it's got to be the square root of both components squared. Correct, class? Y'all with me? All right. Now, if you've got that, now I say if I have a little chunk of charge here, dq, which would be equal to the charge density times a d phi. Y'all, charge density, a d phi is what? The tip of that wiper arm, right? D phi would be the differential amount of angle I would move to get this. Y'all with me, class? We're going to be in cylindrical coordinates. If that's dq, then I can say my dv is equal to dq over 4 pi epsilon naught over r, which is going to be square root of a squared plus c squared. And furthermore, I can replace dq with what it is, and I can say it's equal to rho L times a d phi right here, and then it's divided by 4 pi epsilon naught square root of a squared plus z squared. Y'all agree with that? Just the differential amount of charge over 4 pi epsilon naught divided by the distance, not distance squared. Y'all follow me? This is voltage. Now, if you get that, and I wanted V, I want you to take a look. Just for a second, don't do anything. Just look here with me. When I integrate this to get V, I integrate from 0 to 2 pi, don't I? Right? I have to go all the way around the loop. 0 to 2 pi. Well, is anything in here a function of phi except d phi? Nothing, right? It's scalar. D phi integrated is phi from 0 to 2 pi is just 2 pi, isn't it, class? In other words, the only thing I need to do to get that integral is get rid of d phi and replace it by 2 pi, and I've got that. And when I look, I have 2 pi up top, 4 pi on the bottom, I get 1/2. Then I get rho L here, A over epsilon naught, and then I have this business, square root of a squared plus z squared, and that's the voltage, right? Now it's important that the axis is left in terms of z. It's not at a given point, it's at any point. You all follow me? So now to get the E field from that, that's the voltage. I'll do it over here. to get the E field, I used the definition I gave you, that the E field is equal to minus the gradient of V, right? Now pay attention to this. Here's my gradient of V, right? I mean, I've done this in Cartesian, but it'll be the same as in cylindrical. Because the only component in cylindrical, you would have a dV d rho. Well, you're only moving up and down the axis if you're talking about the E field on the axis, the only variation is going to be in Z. A is fixed. Do y'all follow me in that class? You're not changing that. So when you take this gradient operation, the only thing that'll survive is dV dz. So this is equal to dV dz. Now you can look in your book, minus dV dz. Well, what is dV dz? Look over here. Here is V. When I take a derivative of this with respect to Z, what do I get? I get all this stuff, and then I have to take a derivative of 1 over the square root of a squared plus z squared, right? What is that? So I get E would be equal to what? Minus, and then the fun begins, rho L A over 2 epsilon naught. And then I have to take a derivative of 1 over a squared plus z squared. Well, that's going to be a squared plus z squared to the 3/2, right? Then a minus sign will come out, right, because it was on the bottom. And then what else? Well, you're going to get a 1/2 technically out front. Then you have to take a derivative of the inside with respect to z, correct? Which is 2z, right? The derivative of this would be 2z dz. And then you get 2 and z. Well, these two cancel. The 1/2 and the 2 cancel. So you get that. And that right there would be in the AZ direction. And that E is the electric field. There's supposed to be an A and a Z here. A is the radius, Z is the altitude. And that is the electric field we got by doing the integration and making arguments of symmetry. Now, I know I didn't have enough time to really establish this fact in your mind, but it's a whole lot easier to do V and take a derivative than it is to do integrations. And I'm telling you with computer programs that I write stuff, it's much easier, orders of magnitudes easier to do that. I'll give you some homework. I'll tell you what, I'm gonna not do a quiz on Monday, I wanna do it on Wednesday possibly. We may do a Wednesday, Friday quiz sequence, all right? But I wanna establish you in this voltage business. I wanna make sure we're clear on that. I'll give you some homework, please do it over the weekend. If you have